This video is for topic 31, simplifying nth root radicals. Now, we have simplified radicals before. Way back in topic number 17, we were working predominantly where roots had an index of 2. We approached this with two methods, either using prime factorization or multiplying by perfect squares. Most of us were in the camp of utilizing our prime factorization factor tree and then looking to group out pairs of numbers to pull them outside of the radical, leaving anything that wasn't in a pair inside the radical, and then multiplying everything outside, multiplying everything inside, and coming up with our simplified answer. We are going to use that same approach as we move to higher indexed roots. So let's go ahead and start with factor tree for 432. Even number, clearly divisible by 2. 216 divisible by 4 and 54. 4 is 2 and 2. 54, 6 and 9. 6, 2 and 3, and 9, 3 and 3. Giving us a prime factorization of 2 times 2 times 2 times 2 times 3 times 3 times 3. Now, applying this to what we've already done with simplifying radicals that in fact are square roots. Notice here the index is not given, so we can assume it to be a 2. If we think about 432 in its prime factorization, we're looking for pairs of numbers, or a group of 2 in order to come outside of the radical. So I have one set of 2's. Here I have another set of 2's, 2 to the first, and we can pull out a set of 3's, leaving us with just a single 3 underneath the radical. Multiplying everything outside and multiplying everything inside leaves us with our answer of 12 square root of 3. Okay, taking the same prime factorization and now looking at the cube root. Well, with the square root we were looking for groups of 2, with the cube root we're going to look for a group of 3 in order to come outside of the radical. So, thinking about this then, instead of grouping up 2 sets of numbers to pull out, we need in order to have 3 numbers in order to come outside of the radical. Here we're able to grab a group of 2 and a group of 3, leaving us with just one single value of 2 stuck underneath the radical. Multiplying everything outside and everything inside gives us an answer of 6 cube root, or third root, of 2. Okay, if with square roots we look for groups of 2 and cube roots we look for groups of 3, if I'm given a fourth root, I'm going to look for groups of 4 in order to pull outside of our radical. Fourth root. So here I can pull out one set of 2's, but everything else doesn't have enough. I don't have enough 3's to make it, so all of them are going to stay inside of my radical. Multiplying everything outside and inside to fourth root of 27. So this one number gives us 3 very different answers depending upon what root index we have. So be mindful of that moving forward. Okay, a quick note now that we've introduced other indexed roots instead of just the square root or even. When we were simplifying negative even roots, we dealt with negatives that were underneath the root by thinking about the square root of a negative number as being represented by I. And then we went about our business simplifying like we had done before. So when we did the example square root of negative 50, we imagined the square root of negative 1 as I, and then simplified the square root of 50 like we normally would, and just paired up 5 root 2 with the I. This is going to be different when I have the negative odd root. So when I take the odd indexed root of a negative value, we're going to interpret the odd root of negative 1 not as I, but we're just going to interpret it as a negative. This comes from the idea that if I were to take and multiply together a negative value 3 times, for instance, thinking about the cube root, when I multiply a negative by a negative, it turns into a positive, but when I multiply again by another negative, we actually get a negative value. So this is going to kind of bypass. There's no need for us to use imaginary values. It's just going to be negative. So looking at the cube root of negative 108 and thinking about it as negative 1 times 108, or the cube root of negative 1 times 108, we're going to interpret this cube root of negative 1, well, that just is a negative value, or a negative 1. And we're going to go ahead then and simplify the cube root of 108, just like we have in the past. So made a factor tree for 108, which means I can then interpret 108 as 2 times 2 times 3 times 3 times 3, all underneath the cube root. Again, cube root meaning that I need groups of 3 in order to come outside of the radical. So I have 1 group of 3 can come out. So just list it as just a 3. And then this 2 and this 2 are going to be stuck on the inside. So simplifying those down, multiplying things outside and multiplying things inside, gives me a value of 3 cube root of 4 as my simplified cube root of 108. Now, all I need to do is multiply, again, things outside the radical and things inside the radical, which gives me my answer of negative 3 cube root of 4. If you want to go ahead and give the fourth root of negative 80 and the cube root of negative 72 a try, using these as examples, I'll reveal the answers in 3, 2, 1. We get an answer. Fourth root of negative 80 is 2i, fourth root of 5. And for 3, the cube root of negative 72, we get negative 2 cube root of 9. Taking a look at the work there, doing the factor tree for each, dealing with the negative first, either turning it into an I if it's the square root, if it's an even indexed root, and turning it into a negative if it's an odd indexed root. And then dealing with the root just like we had done before, looking for groups of numbers to come outside of the radical, leaving anything that is not in that particular group inside, multiplying everything outside, multiplying everything inside. Okay, now applying this to just numbers is what we've done up to this point in time. Let's go ahead and see if we can apply this to variables. Now, when we apply it to variables, it's often helpful to think about the connection between radicals, which we've been dealing with, and fractional exponents, or what they're called as rational exponents. So the way we can interpret a radical with an index of n, and anything that has any exponent underneath the radical, let's say with exponent of m, we can interpret this as the fractional exponent m over n, or the exponent is in fact in the numerator of my fraction, and we would say then that the index is going to be in the root is going to be in the denominator of fraction. So bouncing back and forth between these will actually help us in terms of interpreting what's actually going on with the variables and how to deal with them. So if I was given the fourth root of a to the fifth, I can interpret this as, well, the index and the exponent. I will interpret this as a to the fractional exponent of the exponent will become the numerator. So we're going to have 5 over the index, which is the denominator of 4. Power over root. Looking at b, here I must remember that the exponent here is technically a 1 on my value of b, and we see that the index is 3. So interpreting this then is b raised to the fractional exponent of 1/3. Power over root, exponent over root. We can go backwards with this notation as well. If I wanted to actually write this in radical form, we can then say, all right, I have a radical. Well, the exponent is in fact going to be 3, the numerator, and our index of our root is going to be a2, whatever the denominator of our fraction is going to be. One more example here going backwards. I'm going to find the somethingth root of d raised to some exponent. Well, the exponent in this case is going to be 4, and the root is going to be 11. The 11th root of d to the 4th. Okay, pause the video for a minute and go do in your delta math for today. Go ahead and try exponential and radical form, converting back and forth between these, just very similar to these 4. Go ahead and try those, and then let's go flip to the back side of these notes. Okay, putting these ideas together of simplifying a radical with just a number and simplifying a radical with a variable, turning it into this fractional exponent, we can go ahead and try to solve, and we're able to solve radical problems that look like this, simplifying radical expressions that look like this. For our mastery check, we're going to be going ahead and trying and doing simplifying nth roots, simplifying algebraic square roots, so that would be an index of 2, and then simplifying algebraic cube roots with an index of 3. So focusing on square and cube roots for just the practice, knowing that we could go to higher roots if possible. So that's what our mastery check is going to be on. Looking at these examples though first, let's go ahead and try 2 together. We'll start off with the square root. Notice that our index isn't listed, so we know it to be, assume it to be a 2, of 16x y to the 5th. Now, right off the bat, let's go ahead and interpret this as the number and then the variable. Just to keep them clear in our brains, it's a lot easier to do that. Starting off, what is the square root of 16? Well, no fancy prime factorization needed here. We know this is just a value of 4. Square root of 16 is going to be 4. Okay, well, let's go ahead then and interpret the variables. Let's turn these into fractional exponents, where x is raised to the 1st power and y is raised to the 5th power, and they're all underneath the index of 2. We can say that x is raised to the 1/2 power and y is raised to the 5/2 power. So thinking about it as a fractional exponent, this allows us to kind of think about, all right, well, how many groups of 2, or how many 2's are there in 1? How many groups of 2 are there in 5? Another way to think about this is we're turning these improper fractions into mixed numbers. So 1/2, well, that just stays 1/2. 5/2, though, would turn into 2 and 1/2. 2 full values and 1/2 left over. So how does it help us? Well, the whole numbers are how many values that are going to come outside of the radical, and the leftover exponents are what's going to stay inside of the radical. So looking at that, then on my x values, my 1 did not reduce. I didn't have any whole numbers, so that x to the 1st just was trapped underneath the square root. However, with my y to the 5/2, we had 2 full y values that could come outside of the root, and we have 1 trapped underneath. So putting all of these pieces together then, we can go ahead and multiply everything outside and everything inside, giving us 4y squared to the square root of x to the 1st and y to the 1st. We have the distinct outside of our radical and inside of our radical separation. Okay, let's go ahead and take a look at this next example. Notice here there's already stuff outside of the radical, so we're just going to ignore it until the very end. So in terms of our last steps, if I was doing a parallel here, I'm going to go ahead and write 2y all the way down here at the end, and we're going to multiply that with whatever our answer from our radical is going to be. So interpreting this as the cube root of 88 times the cube root of x squared y to the 9th, again, that 2y just sitting along until we can do something with it, we can go ahead and simplify the cube root of 88 as 2 times the cube root of 11. All right, let's go ahead and interpret these these exponents underneath as fractional exponents to help us simplify down. So x to the 2/3, y to the 9/3. Simplifying these down, 2/3 is just 2/3, but 9/3, well, 9 divided by 3 is just a 3, and there is, well, nothing left over, so we don't really have that extra fraction there. So in terms of interpreting this then, we have 2/3, so the x's aren't going to be able to escape from underneath the root, but our y's are going to be able to escape. 3 sets of y's are going to come out, and we're going to have none left over underneath the radical, giving us y cubed outside of the radical. All 3 y's escaped, leaving us no y's underneath. Those 2 x's couldn't come out. There's only 2 of them, and needing a group of 3, so that x squared stays underneath. So we're going to go ahead and regroup this, multiplying everything outside the radical and putting everything inside the radical together, along with that original 2y from where our problem started outside. So we have 2y, 2, and y cubed outside the radical, and 11 and x squared inside of the radical. So giving us a finalized 4y to the 4th cube root of 11x squared. Again, we had 1y here, 3 y's there. 1 plus 3 gives me 4. 2 times 2 is 4 for the values. And then everything under the radical. Couldn't really do anything other than just list them next to each other. Okay, if you want to go ahead and try 2 more problems before you go ahead and do our mastery checks, I'll go ahead and put the answers to these problems up here momentarily. Otherwise, please go ahead and work on simplifying nth roots, algebraic square roots, and algebraic cube roots on Delta Math. Get 5 correct for each, no penalty. Here are the answers to those last 2 problems with the worked out for us.